Hey guys, what's up? Riccardo here, and today we've got another tutorial on circular motion, and more specifically, deriving the minimum height and velocity required to complete a vertical loop. So, let's dive right into it. For this sort of problem, we're going to need to know a few concepts. The first concept is conservation of energy, and so this concept states that in a system, the amount of energy is always constant, and so the energy initial equals energy final. And with problems with vertical and horizontal motion, we'll have m1gh1 plus half m1v1 squared will equal m2gh2 plus half m2v2 squared. So basically the potential and kinetic energy will remain constant within a system. And so obviously, if you, let's say, relevant to this example, at the top of a roller coaster about to start, so you're stationary, you can ignore the kinetic energy because V will be equal to 0 and cancel out the term. Or alternatively, if you're down the bottom of the loop and there's no H, it cancels out the term and you're left only with kinetic energy. So, second concept for the day, circular motion, obviously, because we're dealing with a vertical loop. And so the formulas we're going to need to know for this, well, first we'll draw out the circle, make it a bit easier. So we can do this. So in a circle, and when I say I have an object, let's say it's tethered, for example. At any time, the velocity will always be tangential. And so we'll put velocity, and the acceleration is always inwards. Acceleration centripetal. And so as the acceleration is inwards, the resultant force is going to be inwards. And so centripetal acceleration is equal to v squared on r, where r is the radius of the circle and v is the velocity. And so as you know, force equals mass times acceleration, which is mass times, in this case, v squared on r. And here we have the formula for the force of centripetal motion. And so this is a net force, and that'll be important when we get on things a bit later on. Alright, so here's the problem. At the top of this little hill with height h, we have our little dude looking very excited to go down on his roller coaster ride. So he's going to come down here, he's going to hit the loop, and if we plan it all right, he's going to make it around safely with no bad endings for anyone involved. So the questions are, what's the minimum velocity he needs up here to ensure that he doesn't go kersplat, and what's the minimum h here required in order to achieve that velocity? Pause it here if you want to give it a shot yourself, and if not, we're going to dive right into it. So first we're going to start with a free body diagram. As you can see, here's my poorly drawn circle with our dude looking a bit scared. So at the top of the circle, if he's going fast enough, the guy's going to have, well, obviously the force of gravity pushing down, and also a normal force because he'll be in contact with the surface of the circle. Now, the slower he goes, the less contact he's going to have with the circle, with the loop. And it's going to get to a point where he's just about got no contact, and any less than that, he's going to fall off the loop and it's going to end very badly. So in order to solve this problem, the only force that's going to be acting is going to be mg, because we can assume that the normal force is just 0 in order to find the absolute minimum required, velocity required. And so if it's just mg, the only force acting is mg, so that's the net force. Now, mg then is going to equal the force of a circle, force of circular motion rather, which would be mv squared on r. Now obviously we can cancel the m's, and we get that g, acceleration of the circular motion, is equal to v squared on r, and that's what we got before with the acceleration centripetal, v squared on r. So let's dive into the actual derivation, shall we? And so, we have g equal to v squared on r. Now, the first part of the problem is relatively simple. We just got to rearrange this equation in order to isolate v. So, obviously then, v squared is going to equal to gr, if we just put the r over, and v is going to equal to the square root of gr. Now, the next part. At the top of the loop-de-loop, if we go back, you can see that he's stationary, and he's only going to have potential energy due to gravity. While if we go up to the part here at the top of the loop, he's going to have both potential energy due to his height of 2 radius above the ground, but if he's moving, he's also going to have kinetic energy due to his velocity. So now with that in mind, we know that m times g times the h, we can ignore the kinetic energy on this part because he's stationary, is going to equal to half mv squared plus mg. Now the h on this side of the equation is going to equal 2r because that's the diameter of the circle and that's how high it's going to be at the top of the loop. Mg 2r. Now doing some rearranging, we can cancel the m straight away. Cancel that, and we get gh is equal to half v squared plus 2gr. Now, do you remember that we have v squared here is equal to gr, so we can just substitute that right in, and we can get gh is equal to half gr plus 2gr. Now, eliminating g's, let's get them all out, we'll end up with h is equal to half r plus 2r, which is equal to 2.5r. So in other words, h is equal to 2.5r. So there you have it. You've got v is equal to gr, root gr, and h is equal to 2.5r. So that's basically the derivation. We're going to go into a quick practice problem now, just to test the understanding. And so here we have a little loop-de-loop. No drawing of the cart this time, I'll just add it in. A little man again, he's keen. And we have a radius of 10 meters. So the first question is asking, what's the minimum velocity required in order for him to make this loop, and what's the minimum height needed at the beginning to achieve that velocity? Well, we want to pause it if you want to go into it now, but we're going to jump straight into it. Just going straight from our formulas, remember that v is equal to root gr, so radius of 10, g will simplify to 10, 10 times 10 is 100, root 100 is equal to 10. So the minimum velocity will be 10 meters per second. And what's the minimum h needed? Well, if we remember, the minimum h needed is equal to 2.5r. We can go back, we can see that. Yep. And so if the radius of 10, 2.5 times 10 equals 25 meters. And so we need h here to be 25 meters, and we need the velocity at the top of the circle to be 10 meters a second. So that's basically the derivation and application. Now, for any of you that want to sort of conceptually understand why this is, I've just got a little extra slide here. And because I always had trouble understanding why at the top the cart didn't just fall. Because even if he was going fast enough, I never fully understood, because all the forces are still acting down and there was no upward force. And so I could never really conceptualize how it is that the cart didn't just fall down. So I've come across a few of these diagrams in my textbooks, and I think they're really useful in sort of getting a conceptual gist of it. And so I like to first eradicate the circle, so we can ignore this yellow circle now. Just imagine the cart at this point here, and imagine it with, let's say, a large velocity with this blue line. With this large velocity, the cart is going to fall down because the net force is down, so the net acceleration will be down. But since its velocity is so fast, the cart is going to go a long distance as it falls down. It's not going to just fall down immediately, it's going to take a while, and the arc is going to be a lot longer. However, if you've got a small velocity, that arc is going to be much shorter and it's going to fall down far sooner. So with now this sort of idea in our heads, if we put back the circle, we can see that with this larger velocity, the cart is going to hit the circle before it has a chance to really fall down, and it's going to keep doing that until it's back on safe territory. While with the smaller velocity, well, the story doesn't end too well. Since the velocity is much shorter, the arc length is much shorter as well, and the cart will fall down before it gets a chance to reach the circle. Now, that's basically it, guys. I hope you enjoyed the tutorial. It's a bit of a short one this time. Let me know any ideas of any other concepts you guys want made clarified or have some problems worked through. And also let me know any feedback on how to make the videos smoother and nicer. Until then, guys, happy studying.